So welcome everyone to another Thursday Astrophysics seminar here at the Institute. It's my pleasure today to introduce our speaker, Professor Eric Gawiser, who's visiting us on sabbatical this term. Eric is a distinguished professor in the Department of Physics and Astronomy at Rutgers, not too far away at the State University of New Jersey. He actually started his career as an undergraduate here at Princeton, where he studied physics and public policy, graduating in 1994. And then he hopped across the country to the Bay Area to go to grad school at UC Berkeley, where he worked with Joe Silk, among others, on cosmic microwave background physics, earning his PhD in 1999. After that, he began to use the world's largest telescopes to study distant galaxies as a postdoctoral fellow at UC San Diego, and later a National Science Foundation AAPF fellow and Andes fellow at Yale University. Afterwards, he joined the Rutgers faculty in 2007 and has studied galaxies, stars, and black holes to understand how these objects form and probe, and how they can be used to probe fundamental physics ever since. Eric has obtained support from NASA, the DOE, the NSF, including an NSF Career Award, and was recently actually named a fellow of the American Physical Society for his exceptional accomplishments and leadership in the study of galaxy evolution and cosmology. Eric is also involved in a very large number of cosmic surveys, which is where I met him initially in the context of Rubin LSST, many others, including HETDEX, Candles, Simon's Observatory Music, and Odin, which is the 100 square degree DCAM, so there's an acronym inside the acronym, Imaging and Narrowband Survey, which I believe is what he's going to tell us about today in his talk about what we think we know about Lyman Alpha Emitting Galaxies. So please join me in welcoming Eric, and I'm very much looking forward to your talk.
Thanks so much, Nick. Thanks to Nick for that lovely introduction. I really wanted to thank everyone for being so welcoming, friendly, and hospitable in the days I've been here so far. I'm looking very much forward to the rest of my sabbatical visit. I titled this What We Think We Know About Lyman Alpha Emitting Galaxies, which, as Nick mentioned, are a topic dear to my heart. I'd like to title it What We Know, but I thought perhaps a dose of humility would be helpful. And you'll see what I'm going to do today is to try to give you an introduction to the subfield that I work in, or at least one of them, and along the way, give you a sense of where some of the common wisdom probably should be modified, especially as we confront it against new and better data and improved measurement techniques. So let's start out by providing an introduction of what we mean when we talk about Lyman Alpha Emitting Galaxies. In this case, we have a classical model that you can see was given to us from on high. Partridge and Peebles in 1967 postulated that if you just imagine the Milky Way in its formative stage, and they were imagining like the whole Milky Way, not a bunch of small pieces coalescing in those days, then it would be 700 times more luminous, but with no dust, you'd have a huge burst of star formation whose Lyman alpha photons could escape, and you should see significant Lyman alpha emission. So it's essentially recommended to search for primordial galaxies through Lyman alpha emission. I'll describe in the next slide how long it took for that to actually work, but the idea had a lot of merit. These Lyman alpha emitting galaxies, even in their conception, and they turn out to be, are young, low-mass star-forming galaxies with very low dust content along the line of sight. This is because Lyman alpha photons resonantly scatter. So if you have a little bit of dust, the Lyman alpha photons see a very big column of dust, and they tend to get extinguished before escaping the galaxy. The distinct emission line signature of this strong emission line from neutral hydrogen makes them easily detectable. I should put easily in quotes. You'll see again how long it took. And we can collect large uniform samples and probe the high-redshift universe statistic. So the common statements that I promised you in my abstract I'd cover, I'm going to go through these 5 today that are about Lyman alpha emitting galaxies. I'll go through each in turn, but let me, as a form of outline, show you what these are. I actually like sometimes in talks to start by showing what my conclusions are going to be, so the audience knows what to expect. In this case, when we get to the conclusion slide, it's going to look like this, but copy edited, so that we can say what the right, more accurate statements probably are. So something that's commonly said is that LAEs are young low-dust galaxies and undergoing initial bursts of star formation. That's close to what I told you in the previous slide. Certainly was the Partridge and Peebles idea. The second statement that due to resonant scattering, Lyman alpha photons experience much higher dust extinction than UV continuum radiation. That stands to reason from basic physics, but is it really happening? The third, that LAEs lie in the same correlation between star formation rate and stellar mass as other star-forming galaxies at the same redshift. We'll explore that. The fourth, that a galaxy's observed Lyman alpha emission has a rest frame equivalent width, which I'll define for you, greater than 240 angstroms possesses a top-heavy initial mass function, likely from population 3 stars. This one turns out to be pretty interesting. The final one here is that Lyman alpha emitters at redshift less than 6, at least, before we have significant impacts from ionization, are faithful traces of a large-scale structure and can be used to constrain cosmology. I hope so. There are big cosmological surveys, as Nick was mentioning, that actually are relying on Lyman alpha emitters as their probes. So the first statement here, that LAEs are young, low-dust galaxies undergoing initial bursts of star formation. As I mentioned, that was the initial concept behind Partridge and Peoples' proposal. Observational success happened 30 years later in these two papers with Esther Hu, Len Cowie, and collaborator, and Richard McMahon, at redshifts of 4.5 and 3.4, a very impressively high redshift in those days. We might be, a little numb to this in the era of JWST, but this was a very rapid jump out to quite high redshifts in the 90s by this technique. The samples were very small, but the technique turned out to work. And then about 10 years later, we applied spectral energy distribution fitting to Lyman alpha emitters, and we're able to directly show that if you look at their stacked spectral energy distribution, there is indeed no evidence for significant dust with like a reddening an extinction in AV of less than 0.1 magnitudes. So that's a consistent story. A year later, in related work coming from the music survey that Nick mentioned, we applied a 2-component fit to the stack photometry, trying to be a little cautious, like if you just do a single component fit to star-forming galaxies, you're gonna find that they're actively star-forming and therefore young. But if you allow there to be an older component, is there evidence for that underlying it in the spectral energy distribution? And in this case, there sort of was. The young component at an age of 20 million years, wow, that's consistent, but only 20% of the mass. That doesn't sound like the first burst of star formation. And indeed, solutions with 100% of the mass in a young population, not quite as young as 20 million years, were allowed. So really, we couldn't answer the question at that stage. There have been major methodological advances since then in spectral energy distribution fitting, including the direct reconstruction of star formation histories from broadband photometry, which was not possible until recent years. And that motivates re-examining this question. So just to set the stage a little bit further, I'll point out that, like a typical professor, I've phrased this talk in very much a review of the field kind of mode. That will turn out like a typical professor to be a thinly veiled facade for telling you about my own research, made somewhat more palatable by repeated shameless promotion of junior members of my research group. To that end, the cast that is responsible for all the achievements that I'll talk about for my own group today are these folks. In particular, I've bold-faced Nicole Firestone, shown here, and Danisbel Herrera, who I don't unfortunately have a picture of right now, and they're doing the work on Odin that you'll see their names on papers that are both out and in preparation. The Odin survey. I won't try to repeat the acronym, but I will point out for those who are worried about the compound acronym that stands for the dark energy camera on the 4-meter telescope down at Cerro Tololo in Chile. This is a survey program approved by NORLab, the NSF's optical and infrared astronomy laboratory. And we're actually in our last formal semester of data taking right now. So we've taken most of the data and actually reduced it. We're using this dark energy camera. We built 3 custom narrowband filters for the camera at these 3 wavelengths. These are narrow filters. I'll show you in a picture in a second. That corresponds to these 3 redshifts and then these 3 epochs. You can notice the main survey design is to do epochs separated by 700 million years at this time, roughly 2 billion years after the Big Bang. And then we get these 3 different samples to do evolutionary studies across cosmic noon, the so-called era when overall cosmic star formation was at a maximum. Yeah.
Is 700 million years a specifically interesting timescale for these objects?
I think we're going to find out. It wasn't based upon some prediction that that is the lifetime or something like that. It was basically based upon observational feasibility that, okay, we can split the optical wavelengths into 3 filters that at least have a constant delta T. You could add a 4th one up at a redshift of about 6, but the higher you go in redshift, the more sky background you get, the further away the objects are, the harder it is to get a large sample. We wanted large statistical samples of these galaxies. And we are pairing with broadband data. As I'll show you in a moment, we need both deep narrowband images to see the emission line of Lyman alpha. and also broadband images to know that this object is much brighter in that narrowband than in the broadband. Otherwise, it could just be a very bright continuum object from one image alone. And so we have the archival broadband data in hand from the super strategic program. The Claude survey adds U-band data in some areas. And then this whole survey is designed by covering all 5 LSST deep join fields, that once even the first year LSST data release comes out, we'll have deeper broadband data than we've ever had for this kind of emission line galaxy science. And that actually will introduce a few other analyses beyond what I can show you today. So here's the plot I've promised a couple times of our filter set. It continues with the Z and Y band. And what we're showing here are 3 narrowband filters. Notice there's always a broadband filter that should get some light, even if this galaxy had a pure emission line and no continuum at all. That will become useful at one point. But basically, here's a template of a Lyman Alpha emitter. There's a strong emission line. And if it happens to fall in one of these 3 narrowband filters, we'll notice a much higher flux density in the narrowband filter than in the overlapping or neighboring broadband filters. We can get fooled in this business by using just one broadband filter if an object is very red, or sometimes if an object is very blue, depending on where that filter is. So we always use 2 different broadband filters and essentially interpolate or extrapolate to predict the continuum brightness of the galaxy at the location where we've seen evidence for Lyman Alpha in the narrowband filter. And then we basically form a color between the narrowband and broadband photometry to make sure that there is an excess flux density in the narrowband. That's what triggers the detection of a Lyman Alpha emitter.
What time interval corresponds to the width of these individual bands?
Great. It's delta Z of about 0.06. So it's nothing, it's of order 100 million years, depending on which redshift you're at. Yeah. No, the epochs are 700 million years, but the filters, you can sort of see the filter width is much less than that. Great. By the way, I'm very happy to take questions I purposely designed a talk with only 35 slides, so that there's plenty of time.
You had only 3 narrowband filters. There could be reason why you had chose 3 filters.
Yeah, they're expensive. Like $100,000 each. So it would have been a much bigger project to do more. And also it's taking us 100 total nights of observing time to get the images we want across 100 square degrees in these 3 filters. Adding more would just make it an even longer survey. All right, so that's the selection idea. Oh, and as Nicole Firestone termed this, we have this hybrid weighted double broadband continuum estimation technique. I think you can see why we didn't turn that into an acronym. But the main point is we always use 2 broadbands, and then the hybrid weight is a nice innovation where if an object is bright, we average in magnitudes, approximating a power law spectrum. But if it's very dim, many of you know magnitudes are horribly behaved if you barely detected an object. And so then we average in flux densities. So we switch based upon the signal to noise, and that turns out to work pretty well. Oh, and again, no continuum detection is required. That makes this whole Lyman Alpha emitter selection technique completely complementary to the selection of Lyman break galaxies or any other high redshift galaxy selection technique. So these are the color magnitude diagrams at our 3 redshifts that we're using to find the objects. They look nicely consistent with each other. The exact way we form this narrowband excess color depends upon which narrowband we're using, corresponding to the redshifts, and then it's just plotted against the magnitude in that narrowband. Again, the objects can be arbitrarily dim in the continuum, which would just move them up this plot. That's fine with us because we're selecting objects above the horizontal dashed line, which corresponds to a fixed definition of 20 angstroms equivalent width in the rest frame for the Lyman Alpha emission line. And that's just the traditional definition. It means we're selecting the same sorts of galaxies at all 3 epochs. The way these are depicted might make it look like it's a bimodal distribution, but that's misleading. The objects down here are a random subsample of our catalog. Almost all the objects in the catalog are down here. And then above the dashed line, every object in our catalog is shown. So we're really looking at the tail of a distribution when we select the objects. You can see the vast majority of objects selected are up here. They're very dim in the narrowband, but we still detect them. And then they have significant excess flux density in the narrowband compared to those broadband filters, revealing an emission. We want to eliminate objects that are very bright in the narrowband, like magnitude 20 or brighter, because they're probably quasars instead. We do have residual AGN contamination, but they're not too numerous. We do eliminate objects that have very large radii, both because Lyman alpha emitters of these redshifts are known to be quite compact, and because if we have very large extended objects, we know that our photometry is often messed up for those. So we get systematic errors. And then we ensure that the emission in the broadband filter that overlaps the narrowband that had the detection is at least as high as we would expect for a pure emission line galaxy. This is the point I was making before, that if this emission line is arbitrarily high and there's no continuum, I should still get some flux density in the broadband filter. If I check for that, subtract 2 sigma, and I still don't see it, I probably have a spurious contaminant, which is something we worry a lot about. It's sort of a bane of this whole field that if you have a fake detection in your narrowband image, and then you do the aperture photometry in the broadband images, you won't detect anything. You'll say, that's fine. These objects can be arbitrarily dim in the continuum. And that was spurious. So you want some way to get rid of them. And we've come up with that. Yeah.
Are there any interloping lines that you have to worry about?
Great question. Absolutely. You notice I carefully said at one point we have an emission line detection. I didn't necessarily say it was a Lyman alpha detection. So this technique works very well at this redshift where the interlopers that might trigger an emission line tend to be a few AGN and they're rare. Oxygen 2, it is possible, but it's a very low redshift. There's not a lot of volume for oxygen 2 emitters. Here we worry about oxygen 2 emitters, but we've been able to show over the years that this height of the dashed line, this equivalent width threshold, eliminates almost all of the oxygen 2 emitters. Oxygen 2 emission lines don't tend to have a very big equivalent. Once we get to redshift 4.5, it gets fun. And that's because now we have oxygen 3 interlopers. And oxygen 3 emission lines from galaxies can have arbitrarily high equivalent widths, just like Lyman alpha. But one of the things that Nicole Firestone's done a wonderful job of is developing a color selection that adds to this. We basically take our sample, go into a color space, and know which regions look like the oxygen 3 emitters. We also have a selection for oxygen 2 emitters there, but that's more for being able to study them. We remove an important fraction of the initial sample here as is oxygen 3 emitters by using a color diagram in addition. And in fact, that's reflected in this table where we walk through the different stages. So these Odin catalogs are really large. They're of order 1 million to 2 million objects in each of these narrowband filters that are detected. And that's because we're using a 9 square degree version of the cosmos field. It's much larger than the even formal cosmos field from the Cosmos survey. It's the size of the LSST deep drilling field that's coming soon. And then we star mask, which removes a noticeable fraction of objects. That's basically eliminating regions around bright stars where you shouldn't trust your object detection or your photometry. We do data quality cuts beyond that, mostly getting rid of edges that weren't actually deep enough to really trust. Then LAE selection cuts. And notice that this is where it's a needle in a haystack business. Right? This is where things drop precipitously. We're looking for galaxies in a very narrow redshift slice. And so that means they're a very small fraction of our initial catalogs. Then we do interloper rejection, which doesn't do much except at redshift 4.5, as I answered Nick's question. Now about a fifth of the objects, almost, we remove as likely oxygen 3 contaminants. Reject spectroscopic redshift objects that are known to have the wrong redshift. That has almost no impact. We wish it had more. That has almost no impact because almost no spectroscopy has been done of galaxies this dim, even in the best studied fields in the sky like Cosmos. It's something that we're in the process of improving. And so these are final Lyman alpha emitter samples of 4,000 to 6,000 objects across these 3 filters. To combine that 16,000 Lyman alpha emitters with just one of the Odin fields, we're already almost as large as the largest previously published sample from hypersuprime cam called Silverish. So coming back then to our filter set, now I'm going to show you a median stacked spectral energy distribution of these Lyman alpha emitters. And we did that as a form of validation, just to check, we think we've got very low contamination, but are we right? Now, when you median stack, you get the median, but the error bars are also showing 68% and 90% ranges amongst the sample. So we're able to check those. What you expect to see is a narrowband excess. Those are the blue path checks. That's good. You also expect to see a Lyman alpha decrement at redshift 2.4. Looks like we have one. Lyman break in the U band at redshift 3. Lyman break in the first 2 broadbands, and even you see it in our narrow bands at redshift 4.5. And that was when we were most worried about contaminants, which would not have the Lyman break and would have a bump in Z band when oxygen 3 triggers, and then you get H alpha in the Z band. So we look really good this way. I have a hidden slide with them if anyone cares, but the similar stacks of the supposed contamination samples look like contaminants. So we're really happy with that. Okay, so now let's take spectral energy distributions like the ones I just showed, but of individual galaxies and covering more filters using very deep data. We'll turn out we'll use the photometry from the Candles project and take those spectral energy distributions all the way into star formation histories of the galaxies. We can do that because there's so much information in the spectral energy distribution about the history of a galaxy and its physical properties. Young stars dominate the rest UV. We've got Lyman Alpha shown here. We get an age indicator from the Balmer to 4,000 Angstrom break. We consider the ISM conditions using nebular emission lines. Our overall stellar mass is best probed by how big this peak is, because that's where you get dominated by the old stars, basically M dwarfs. And then if you go far enough, you start to get the dust re-emission, which can be a useful probe, but is not available for very many galaxies, especially this day. And so it's Kartik Iyer from a grad student of mine who put together this plot. The methodology we use to accomplish this is we use the flexible stellar population synthesis, Charlie Conroy's code, to get our spectral templates with well-understood features, add on a cloudy simulation of what the nebular emission and continuum look like. We analyze the spectral energy distribution in tandem with additional features, metallicity, have to assume an initial mass function. We typically use a Calzetti dust attenuation model, and then we model absorption by the intergalactic medium. Otherwise, we wouldn't get those dropout filters correct. We use spectral features to infer the rate of star formation versus time with a novel approach that Kartik developed with me for his PhD thesis called dense basis. And that uses Gaussian processes to fit smooth star formation histories that are very flexible and infer what the star formation history of a galaxy looks like from its broadband photometry. And this gives us a hope of understanding the physical nature of galaxies and their life stories and global properties. I'll show you some examples in a moment. Just as I mentioned before, we use Candles, which was the largest program ever undertaken with the Hubble Space Telescope, to get really deep spectral energy distributions. Because just from the broadband photometry I showed you alone, we wouldn't get a very good SED fit. We'd be entirely in the rest ultraviolet. We wouldn't have enough information. This means we're actually doing this part of our analysis in a much narrower region than the 9 square degrees of the Odin cosmos field. We're doing it in the very small fraction of a degree, square degree that Candles covered, but that's fine. We use dense basis as a non-parametric Gaussian process reconstruction of the star formation history. So this is an observed spectral energy distribution. And we want to model that in terms of a star formation history. It's actually a fascinating challenge in data science because we're after something that is not observed. And that lies in a completely different space from what is observed. So in developing this technique, one of the things we required was that a goodness of fit, a high value for the goodness of fit in the spectral energy distribution space corresponds to a good reconstruction in the star formation history space. We basically tested that with computer simulations. And what we found is that there are a lot of SED fitting techniques from the previous generation where you could get a good fit here and a totally wrong fit here because they assume very simple star formation histories. But in this case, it works out well, and we always track the uncertainties around a median star formation history that we construct. Those are the thin, dark curves shown here, and then we can put an uncertainty band around it. It'll tell you when there's a feature that the code is quite certain about and when there's a lot of uncertainty.
What's the training data for this? Simulated galaxy?
We don't train it.
I don't think.
Right. Gaussian process. So you don't need to train it, but you do need to choose your covariance function carefully. And that's part of what this whole requirement of a good reconstruction SFH space when there's a good chi-squared and SED space.
I guess I meant, but where is this data?
This is a simulated galaxy,
I see.
but the process itself is not it's not supervised machine learning. So that's a good example. And what's shown here is the true star formation history and the reconstructed one. The reconstructed one misses some features, but you can't have everything. The key important part is most of the missed features are still near the uncertainty swath. So we know roughly the star formation history of the galaxy.
Is there a concern that Gaussian processes that you're adopting are sort of overly smooth and can't capture stochastic bursts of star formation?
Okay, great. Not until you said that, but yes and no. So the key problem is the star formation histories that everybody else assumes are so simplified with all sorts of discontinuities that we definitely like the fact that these are smooth. Indeed, the most widespread competing approach is called Prospector, and it uses bin star formation histories. And bins can be nice, you know what they're doing, but it's really just another parameterization that includes jump discontinuities. And realistic star formation histories don't look like that. Then there's a question of, okay, smooth is good, but are they too smooth? And so for some applications, yes. And this is where you want to play with that covariance function of the Gaussian process. And there's actually a couple of follow-up papers that Kartik Iyer has led that look in detail into how you can do this, including using power spectral density of reconstructed star formation histories to try to measure the level of stochasticity in galaxy formation. So it's a quite right avenue for investigation. So now I'll give you some examples with real data, not simulated. So this is the star formation history we construct from this candle's SED. For those who are not used to just looking at these things by eyes, I'll tell you that this is an F sub nu flux density per hertz, and almost no galaxy falls in F sub nu. This is a very unusual galaxy, extraordinarily blue. You immediately know it's going to be very young. There's no such thing as anti-dust, so dust can't even mess that up, we hope. And so this is really like a maximum burst. Recent years, maybe a little bit of star formation earlier. That's the kind of star formation history you naively expect, and that's what we find. Then if it's a little more normal, this is still quite a star-forming spectrum. It's quite flat in F nu, and there may be evidence for some emission lines. It's the template that's giving you the emission lines. It's not clear that photometry has them except for Lyman alpha there and a couple of points here. So we probably have some strong emission lines. And this is a significant burst of recent star formation. The reason that it's blue shaded up to 200 million years ago is because that's basically the timescale we're sensitive to with broadband photometry. Unless you can see individual nebular emission lines, which can trace star formation on timescales as small as 5 million years, then you're really tracing what happened over the last 200 million years, even as now. So that blue shaded region is what we'll call now, because that's the time sensitivity of the technique. And here there's quite strong evidence for some star formation before that. So not all of the mass is formed in the ongoing burst, but it's a strong burst. And then you get a really red SCD like this with a clear Balmer to 4,000 angstrom break from the photometry. And you can see that this is very different from a galaxy undergoing its first burst of star formation. There's non-zero star formation, so we can detect this in the rest ultraviolet. But most of the star formation happened in these two early bursts that are reasonably well constrained. It's cool. Now I will tell you that your neural network is now well enough trained to sort of do star formation history reconstruction by eye in these extremes. And all three of these were examples of Odin Lyman Alpha Emitting galaxies. So they do not all look the same. The next question we want to answer is, how common is it to get this more classic model of a Lyman Alpha Emitter in a first burst, potential first burst, certainly a main burst of star formation? And are all the LAEs like that in the peak period of star formation at the time of observation? But since one of the examples I just showed you was like this, the answer to that is clearly no. It's just a matter of demographics. And so one really nice thing that Nicole Firestone's done is to name these traditional, semi-traditional, and non-traditional, just to have some words to describe them, and then go through in each of our redshift samples and sort. So redshift of 2.4, it's a bit easier to do the SED fitting and star formation history reconstruction here. We just have more bands, and the objects are often a bit brighter in the continuum. And we have mostly traditional, but certainly a couple examples otherwise. When we go to redshift 3.1, a majority are traditional, but actually we're seeing more of this semi-traditional, couple of these very strong early star formation, not at the time of observation. We go to redshift 4.5, the statistics are similar, but we just lose statistics on the whole. One thing that was useful I didn't point out is back here, redshift 2.4, this object here has a spectroscopic redshift that confirms it's really at the redshift we think. And that's very helpful to us because when you look at these, you start to wonder, well, maybe these are contaminants. That one is not a contaminant, and it still has a very different star formation history than you would have otherwise expected. All right, so then we kind of sum this all up by looking at the percentage of stellar mass created now, meaning in that blue shaded region of the last 200 million years. And we wanted to do a comparison sample, essentially a control sample, by including Lyman break galaxies in our star formation history reconstruction. And this was partially to look at whether what we're finding could somehow be model dependent. If the Lyman Alpha Emitter star formation histories and the Lyman break galaxy star formation histories all look the same, then you worry about whether that's just what the code likes to do on the data, or maybe those two populations are really similar. But in this case, we're finding a significant difference between the fraction of stellar mass created in the most recent burst, being higher for Lyman Alpha Emitters than it is for Lyman break galaxies. That's towards what you'd expect in the typical picture of Lyman Alpha Emitters. as undergoing a very rapid burst of star formation. But as I've told you, we can't really say that most Lyman alpha emitters are in their first burst of star formation. It looks like a fair way to summarize is most are in their biggest burst, at least so far. Can't tell you what will happen after the time of observation. And so we're calling that a formative burst of star formation. And that's really the way to summarize what's happening with the Lyman alpha emitters.
What is the impact of the earlier bursts of star formation on the spectral lines?
Great. Yeah, so let's go back to one of the examples. It's easiest to describe with this one. The stellar mass, remember there's that peak at 1.6 micron earlier? That will trace what the total stellar mass formed. And in a history like this, that's dominated by the old stuff. So when you get to here, there's maybe equal stellar mass formed, old and recent. All of that contributes here, and the recent stuff contributes here, and the rest are ultraviolet. When you get to this, there should be much less mass, and that's how it's falling off.
But you attribute these to very particular peaks?
Yes.
How is that identified?
How does the code identify that? So there are age-based features in here that are hard to see, but and they're subtle, but they're there. And so that's how it's able, you can see there's some significant uncertainty as to exactly what's happening. But like with this galaxy, it really sees intermediate age stars and old stars, where old is a redshift 3 old of 2 gigayears. It turns out this technique is actually harder in some ways to do in present day data from low redshift, because our time resolution gets very poor as you go to multiple billion years back in time. Trying to tell a 10 billion year stellar population from a 5 billion year one is much harder than getting 2 versus 1. So in some sense, we get helped by going so early in the universe that we don't have to worry about the really old stuff having that degeneracy. Okay, so let's look at the next statement I wanted to cover. Due to resonant scattering, Lyman alpha photons experience much higher dust extinction than UV continuum radiation experiences. That would make sense. UV photons go through the dust screen once and escape the galaxy towards us. There's some dust extinction, some dust reddening that happens there. But the Lyman alpha photons get absorbed by neutral hydrogen, re-emitted. It's only when they happen to get absorbed into 2s and there's a 2-photon emission that they disappear completely through that radiative transfer. Otherwise, it's random walk until they happen to escape the galaxy. And so they're going to see the same dust many times. All right. How can we avoid that? Well, maybe we don't need to. Maybe it's happening. This, after all, what led Partridge and Peebles to predict that dust-free primordial galaxies would have strong Lyman alpha emission, as opposed to the kind of galaxies we see in the present-day universe that have much more dust. It predicts that the emergent equivalent width, think of that as the line strength relative to the continuum of the Lyman alpha line, should be inversely proportional to the dust attenuation, parameterized as the magnitudes of extinction in the V band. However, the HETEX pilot survey in a paper led by Guillermo Blanc, now 13 years ago, did not find this. They found a better description is that the Lyman alpha photons are seeing the same amount of dust as the UV continuum photons. And there are a couple of possible explanations for that. One of which would be that the dust is present in these galaxies, but is clumpy. Now, this is a very ad hoc model that always bothered me, but something like it might be happening. If your dust is surrounded by neutral hydrogen that's lower in dust, then the Lyman alpha photons, because the hydrogen gradient will tend to bounce off these clouds. They random walk a bit, but they're more likely to go back out following the density gradient of hydrogen before they see the dust. Whereas the ultraviolet photons don't care and they see the dust. It's a pretty clever ad hoc model for how you could produce this. Obviously, it's very contrived. And so the question is, are somehow real galaxies approximating this distribution of gas and dust in a similar way? And that could explain why we saw a similar amount of dust extinction for Lyman alpha photons and UV photons. Another way to think about this is you basically have to get it to the point where Lyman alpha photons only see the dust continuum once. Somehow the ones that at least escape on the line of sight towards Earth from these galaxies are not resonantly scattering in a dusty cloud. So what do the state-of-the-art observations tell us? Well, they may be state-of-the-art, but they don't give us much in correlation. All right. Indeed, the correlation lines aren't even very trustworthy, but that's fine. Those are the best fits to these scatter plots. So this is that dust extinction versus this ratio of line strength to continuum level for Lyman alpha. And we would expect that the dustier things are, the weaker the Lyman alpha lines are. We expect a strong anti-correlation, not observed. Very much like that HETEX pilot survey result. So this relationship suggests the Lyman Alpha photons we observe may not be experiencing resonant scattering, or at least any resonant scattering is in nearly dust-free regions. It's possible the radiative transfer of Lyman Alpha that escapes the galaxy is instead being driven by gas velocities. Right, so if the first gas that Lyman Alpha scatters off of is receding, then the Lyman Alpha photon has a lower wavelength, and it's not going to correspond to Lyman Alpha absorption as it comes back to the galaxy coming out towards Earth. Of course, that's another toy model, but that sort of behavior in terms of the gas kinematics is what it might take to get the Lyman Alpha photons out of the galaxy. Or you could have this clumpy dust. Something is different than our naive expectation here. It's pretty interesting, at least to me. Any questions? All right, so then the next statement is that these Lyman Alpha emitters lie on the same correlation between star formation rate and stellar mass as other star-forming galaxies at the same redshift. I'm talking about the star formation rate. This is the one where I waved my hands early on in the talk, right? Star formation rate versus stellar mass correlation. It looks kind of like this. You can imagine galaxies moving along it as they grow. Their mass increases, their star formation rate increases. The overall correlation has an amplitude that drops as cosmic time increases. And this correlation was first noted by these authors, and in a feat of misleading attention-seeking terminology called a star-forming main sequence, which is a term you will not otherwise hear me use because it just confuses people, because it bears almost no useful analogy to the main sequence on the HR diagram. If you'd like to hear an extended version of this rant, ask them about it over lunch. Sorry.
Can you go back to the previous point you made in the previous slide? So gas velocities, how much of the gas, of the velocity shift you need to enable photons to escape really?
Right. Several hundred kilometers per second.
Several hundred. Cannot be internal turbulence, so it's okay.
Yeah, that's right.
Thanks.
I think that answer is fair. So there are not all galaxies lie in this correlation. There are starburst galaxies that lie above it. That actually sounds a lot like the first burst of star formation type of Lyman Alpha emitters that we found plenty of. And then there are galaxies that fall below it. This kind of object should be like that. It's got enough star formation to still see it. We saw Lyman Alpha emission, but it's mostly old in mass, and the star formation rate to stellar mass ratio is low, what you'd call the specific star formation rate. It's going to lie below this correlation. We know that there are galaxies that lie below this correlation. Essentially, the green valley and then red and dead galaxies lie down here. We wouldn't expect very many Lyman Alpha emitters to be there. So that's our toy diagram. What does it look like with real data? Well, in the literature, people are all over the place in terms of whether the Lyman Alpha emitters lie above the star formation rate stellar mass correlation. That's what we claimed in papers led by Carlos Vargas and Alex Hagen a while back. Or if they lie right on the correlation in the work that leads to the figures I'm showing here from Kusakabe, or if some are above and some are on, as was noted by Santos et al. So it's really not clear. One thing your eye might notice is that this question of whether the emitters are all above the, or primarily above the correlation versus sitting on it, depends on which correlation you believe in, right? So in this work from Kusakabe et al., the red star lies on that correlation, but above that correlation. So it isn't even as simple as just measuring where your galaxies lie. You have to figure out where you think the main correlation is.
How are these lines obtained?
They're obtained from different papers in the literature that looked at general star-forming galaxy populations, did the same kind of spectral energy distribution fitting, measured their star formation rates and stellar masses, and then basically fit either a curve or a power law.
Is this correlation just a consequence of the Kennigan-Schmidt law effect?
It may turn out to be so. There are many papers in the literature that try to explain it.
And at least it goes in the same direction, right?
It goes in the same direction.
It's either sigma to a certain power.
You talk about Kennigan-Schmidt more naturally when you start to do resolved spectral energy distribution fitting on galaxies. And there's a resolved version of this law where you use star formation rate areal density versus star formation rate areal density. And then it's more natural. Now, you'd get the Kennigan-Schmidt law directly if you used H1 instead of stellar mass and looked at the star formation rate areal density versus the H1 areal density. So everything we're doing here is kind of a step removed from that by not looking at the gas reservoir and instead looking at the stellar mass that has been formed over the whole history of the galaxy. But these correlations are something I'm very interested in for my talk. Good. So it matters how you measure the correlation. And indeed, the thing that really worried us about this is these correlations are measured from different types of galaxies than we're measuring. That's okay. Using different methodology. That's not really okay. So the goal we set out to do is to use better data and a more careful analysis where we basically use the exact same methods to analyze the general population of star-forming galaxies as Lyman Alpha emitters and now do a better comparative study. And that's what we've set out to do as part of Nicole's PhD thesis. And so here it's a redshift 2.4, 3.1, 4.5. These are combining that control sample of Lyman break galaxies with our Lyman Alpha emitters. Lyman Alpha emitters are circles. The size of the symbol corresponds to the percentage of stellar mass created now. So these are objects that are very much in formative bursts, and these are objects that have a lot more old star formation than recent. And you'll notice here we're seeing an evolution from redshift 4.5 to 2.4, where we see more of these unusual ones on this diagram with the older star formation. The higher percentage of LAEs lie above the star formation rate stellar mass correlation once we define it using our LBG control sample, but it's not radical. It's sort of like these circles versus these triangles. You could certainly say, roughly speaking, they're on or above the correlation. And then there are some that are just significant outliers below. One of the challenges in fitting a correlation here becomes your treatment of outliers. If you first fit a power law, and then start to throw out outliers, the first fit will go sort of like this because of all the outliers there. So we've been using a bunch of ridge regression and ridge finding techniques to do a better job of that. And we're still working to refine that, which is why this work is still in preparation. Yeah.
I guess it seems like there's a lot of evolution, from this redshift 2.4 to 4.5 sample, even just the number, it was like 6,000 versus 4,000. Yeah. How sure are you that this is physical evolution and not just selections from the higher redshift sample being harder to study?
Great. Yeah, that's a really fair question. We designed Odin to get roughly equal numbers of Lyman alpha emitters to the 3D epochs. I would say 4,000 to 6,000 is totally within the uncertainty of what roughly equal numbers would need. Mm-hmm. So I don't worry about that difference. Mm-hmm. That doesn't tell me that I'm missing something at redshift 4.5 or have extra contamination at 2.4. They are as close as we knew ahead of time based on the luminosity functions. Mm-hmm. What I do worry about, of course, are any evidence for contamination of various kinds in the samples themselves. Mm-hmm. And that's what we've tried hard to root out. We also, I'm not talking about it here, but we have a bunch of DESI spectroscopy in the two lower redshifts that tell us that our purity is at least 80% and possibly 95%.
I was thinking more of completeness than purity.
Oh, there's a funny way in which our DESI spectroscopy also helps us with completeness because they did a more liberal selection for what they put fibers on. And they're finding a bunch of Lyman alpha emitters that we don't have. So we know that we have completeness of only like 60 to 70%. Someone else had a hand?
Oh, yeah, I just wonder, this is a total star formation rate, not the specific.
That's right. Yeah, so you can divide star formation by stellar mass and plot specific star formation rate, and then things are flat instead of tilted. But the problem is you've now correlated your error bars, so I try very hard not to do that. Because we're really measuring star formation rate and stellar mass independently, or close to it.
So this means the specific star formation rate is going down as the mass goes
up? Very slightly. The typical slope, you're absolutely on the right track. So if the slope of this is 1, then specific star formation rate is independent of mass. The typical slope for this is 0.8. So it's a very slight decrease as you go more mass. And it's quite possible this curves over. That's what's been studied at higher masses and more sensitive to at lower overall redshift by Kate Whitaker and collaborators. All right, so the next statement I can talk about is a galaxy whose observed Lyman alpha emission has rest frame equivalent width greater than 240 angstroms, possesses a top-heavy IMF, likely from population 3 stars. That'd be pretty exciting. So finally, I'm going to tell you what equivalent width is. I should have put this slide a little earlier. Equivalent width is the ratio between the emission line flux and the flux density of the continuum. And if I put that in F sub lambda units, that is per angstrom, I get an equivalent width in angstroms, which is the units I want. What that corresponds to vectorially is if this is 0 level and this is the continuum level of my spectrum, here's my emission line. So I've really zoomed in. I basically have to go back and forth this far to get the area of a rectangle whose height matches the continuum to equal the area under the emission. So the equivalent width is the width of continuum it takes to match the flux inside the emission line. It's not a great term, but I don't necessarily have a better one to offer you. So instead, I offer you that illustration of what it is. So the shaded rectangle is supposed to have the same area as the emission line, then that's its width. You can see in the example here, these emission lines are typically only a few angstroms wide. The equivalent width would be a few angstroms. Lyman alpha emitters, we observe equivalent widths as big as 1,000 angstroms in the observed frame. So it means that you basically have so little continuum, you have to go very far left and right to get the same area. We can also use this for absorption lines. If the line comes down, it's the same concept. Just figure out what the continuum level is and match the areas. So you'll see sometimes people are rigorous and they use a negative equivalent width for emission lines. Those of us who work on emission lines, which used to be just how we. And the width of this region is that equivalent width measure. All right, so the equivalent width probes the initial mass function slope because Lyman alpha emission comes from the recombination of hydrogen. Ionizing photons that are leading to those recombinations are dominated by O stars that don't live very long. The B stars dominate the ultraviolet continuum photons at the same wavelengths as Lyman alpha. And so when you're doing an emission line to continuum ratio, you're basically getting a ratio between the number of O stars and the number of B stars. And that's telling you about the slope of your IMF. So that's cool. You'd rather have a longer lever arm in the slope, but you don't. You do the best you can. Now, 240 angstroms in the rest frame is a rough upper limit to the ionizing to continuum photon ratio for a stellar population with a standard initial mass function, along with trivial dust-free radiative transfer of Lyman alpha, which, as we've heard, might not be the best assumption. The population 3 interpretation of a top-heavy IMF must be true because it was published in Nature. So here's an example of that from an admittedly quite interesting paper in 2006. One thing that actually makes this more trustworthy than many papers on astronomy published in Nature is that they were noting 4 different unusual phenomena that had already been reported in the literature and trying to interpret them in terms of a top-heavy initial mass function caused by population 3 stars. That last bit was a leap of interpretation that has not panned out for subsequent knowledge about the redshift 3 to 4 universe, but they're only talking about 10 to 30% of the stars being metal-free, so it's a little hard to dispute. It's a little hard to prove that those aren't there buried in these galaxies. We just have found no further evidence for this. And of the 4 puzzles they mentioned, they've all been slowly explained by other purposes like Wolf-Rayet stars and Lyman break galaxies that are much more pedestrian, but still cool. And the high Lyman alpha equivalent widths, we still don't have spectroscopic confirmations that they're real. So we looked back at this with better data and a careful analysis. And here are the equivalent width distributions from our 3 Lyman alpha emitter samples. It turns out the exponential function is a better fit than a Gaussian to them. So the red curves are what we're paying attention to. But what we're paying attention to most right now is above 240 angstroms rest frame equivalent width, which is a very small fraction of that sample, moderate there, and only a few objects out here. But we have them. And so that is possible evidence that we've got these very big rest frame equivalent widths, which could come from a non-stellar IMF or this clumpy dust model. Turns out that that's another thing. In addition to explaining the radiative transfer, you can get enhanced Lyman alpha equivalent widths from the clumpy dust along certain lines of sight that might be what we observe from Earth. So that's kind of interesting. But we don't want to conclude that unless we can confirm it, because we did a Monte Carlo simulation. What if this exponential distribution was true, but it cut off at 200 angstroms equivalent width? And then I apply all of the noise that happens in measuring these equivalent widths from data. Remember that an equivalent width, it's the flux of the emission line, which is well measured over the continuum level in the denominator. As I told you, these objects don't have to have any detectable continuum. Their continuum level is extremely uncertain. So you put something really small near 0 with big error bars in the denominator, you lose much control over what the ratio comes out to be. And indeed, when we Monte Carlo that, we can produce this many objects formally above 240 from a sample that doesn't actually have it. So there's no obvious way to know until we do spectroscopic follow-up on the high equivalent with candidates and see if they all come down spectroscopically, or we might be able to confirm some. And that's the plan. And the last statement I'm going to cover today is that Lyman alpha emitters at redshift below 6, where we don't have to worry about reionization effects, are faithful traces of large-scale structure and can therefore be used to constrain cosmology. I really hope so, because we made a huge investment in HETDEX to study the baryonic acoustic oscillations using 1 million Lyman alpha emitters at redshifts between 2 and 3.5. And DESI is now planning the DESI-2 effort, which includes a major sample of Lyman alpha emitters at similar redshifts that they're already doing the imaging survey to obtain. We got really concerned about this back in 2011 when Zheng Zhang and collaborators came out with a paper that said that velocity gradients in the intergalactic medium radically alter the spatial distribution of detectable LAEs. It's basically a form of nonlinear bias. It's like a perpendicular effect to the typical Gawiser effect, where it suppresses radial modes and enhances transverse modes. And while that would be really neat to study, it would very much mess up our ability to use the two-point correlation function for pure cosmological constraints. Thankfully, subsequent investigations, in particular work by Christoph Behrens and collaborators, showed that this came from working at a very high redshift where there's a more neutral IGM that has a stronger impact, and not in the earlier work being able to resolve the radiative transfer within the galaxies. Radiative transfer within the galaxies leads to a much more scrambled velocity field of the escaping Lyman alpha photons that the IGM then has a much less coherent effect upon. And it looks like we're safe to study two-point correlation functions and interpret them within large-scale structure. But how about the Lyman alpha emitters in Odin? Do they show the expected behavior of a linear bias on the large enough separations to be the two halo regime? We can look at that. So here is from a paper led by Dani Herrera that's in preparation. We've got in the cosmos field the spatial distribution of the several thousand Lyman alpha emitters at each redshift. There are no pronounced systematic effects that impact our selection that we can see here, but we do see some strong overdensities, indeed protoclusters. We can even recover a known protocluster in the redshift 2.4 sample called Hyperion. And these are unique structures. In a paper led by Vandana Ramakrishnan, who's a grad student at Purdue, we studied the protoclusters and filaments and also their relation to Lyman alpha blobs found in the same fields. So for us, this is ready with a careful random catalog to analyze the angular correlation function. As we do so, we correct for a number of features. There's a related paper led by Martin White that incorporates a careful correction for redshift space distortions. It turns out to make a small effect at the largest scales here. We account for our expected Lyman alpha emitter contamination fraction. And then when you use this kind of angular correlation function, you have to account for the integral constraint. And then we actually obtain good fits whose chi-squared is formally too good at all three redshifts to a simple linear bias model. We're using the purple points within the two halo regime, ignoring the gray points that are at small separations such that they could be subhalo, like within one halo. Of course, this is an angular correlation function. So pairs that are within a one halo separation might not be in the same halo. They can just be projection. But by analyzing that regime separately, we prevent the trance that the one halo term is hurting us. Now, one of the beautiful things about this data is a very clear one halo term coming in at all three redshifts, quite similar across the three, that just begs for high halo occupation distribution analysis. And that's actually something that we have underway. So that lets us measure linear bias factors at all three epochs, at least the black stars in this diagram against the previous literature. We're seeing something reasonably consistent, a nice trend of evolution in the bias. We actually are finding nearly constant dark matter halo masses from that clustering bias that host the Lyman alpha emitters, and that roughly 1% of those halos have Lyman alpha emitters at any epoch. They really are relatively rare, at least in terms of being rapidly star forming low dust galaxies that emit Lyman alpha in measurable amounts towards Earth. And then this is consistent in terms of bias evolution with something we first pointed out in 2007, that this kind of trajectory from here, these sort of galaxies at these bias levels at redshift of 2 to 3 will evolve into L-star galaxies by the present day. So we're looking at progenitors of Milky Way type galaxies in the present day universe, which is a really nice thing to be able to do in terms of understanding galaxy formation.
How are the halo masses inferred?
Halo masses are inferred from the clustering bias. So you know what, it's basically extended Fresh-Schechter or Schecht-Torman. You know what the bias of any given halo mass is, and you integrate up from some minimum halo mass until you get the right bias factor to match the bias we've observed for our clustering.
He's making a strong assumption on the HOD for these objects.
Yes, but it's making a trivial assumption on the HOD. I'm basically imagining that there is one galaxy per halo as I do this. And then I can come back and refine that with an HOD analysis. I think the only place that would really get you in trouble is when we talk about this 1% occupation. If the LAEs were often in multiple satellites in the same halo, then a lower fraction of the halos would be occupied and they'd be multiply occupied. But at these masses, that's a pretty rare thing to do. So we'll probe that with this one halo term.
So this 1% number comes from the number density.
The number density of LAEs divided by the number density of such halos. Again, a simple thing. Any other questions, Mama?
Can I ask you about this claim about the IGM? So as I understand, this seems to be have been resolved in the literature, but what scale of the IGM are we thinking about? I mean, when you say IGM, is it things that are very, very far away?
Basically, it's velocity gradients in the IGM. So remember I was talking about how if you scatter Lyman alpha off of something that's receding, then it will escape through. So it's that kind of thing, right? If there's a coherent flow in the IGM, then the Lyman alpha emitters that are in the right location versus that will be seen by Earth.
What's the mean?
And the ones behind that won't be seen by Earth.
What's the mean, I mean, how far does it how far does the photon travel before it's scattered?
Yeah, usually, well, that's density dependent, of course. Right, so in this case, we're talking impact effects on megaparsec scales. That's not most of the radiative transfer that affects Lyman alpha photons. Again, that early simulation just didn't have the resolution. At some level, it's a failure of modeling as well to really get at the radiative transfer within the galaxies before the IGM could have any. So I just wanted to mention, since I'm here for the semester, other topics you can ask me about. I think very commonly alluded to several of these in the introduction. I've been very active in the LCST dark energy science collaboration and have ongoing work there with cosmological parameter forecasts and machine learning post-processing to improve photometric redshifts to get better tomographic binning for the 3x2 point analysis. Work on the Hubble telescope dark energy experiment, HEPDEX, where we developed the basic method used to separate Lyman alpha emitters and oxygen 2 emitters there. That's all spectroscopic, blind integral field spectroscopy, but it doesn't have the resolution to resolve the O2 doublet. So you have to figure out what's a Lyman alpha emitter and what isn't from other arguments. Work on SEERS with JWST is one of the early release science projects. And there, something I want to work on here is applying these star formation history reconstruction techniques I've shown you to the SEERS galaxies at redshift greater than 5 and see if there's anything we can actually learn at redshift greater than 10 there, which is probably too high to have enough bands to be useful. Work on Simon's Observatory, including in the Engagement Mentoring and Climate Committee, particularly scientifically interested in the cross correlation of CMB and large scale structure. And then anyone who's got a science policy interest is welcome to talk to me, since I was on the APS panel on public affairs. That was rewarding, but also a little frustrating. All right, so concluding statements with copy editing. I would claim that fairer statements, based upon what we've seen today, are that Lyman alpha emitting galaxies are young low-dust galaxies undergoing formative bursts of star formation. That is, most of them are forming most of their mass in the ongoing burst, but it's not necessarily the first burst, and there are exceptions. That despite resonant scattering, Lyman alpha photons experience about the same dust extinction as UV continuum radiation, and that's something we still need to work on understanding. That the Lyman alpha emitters lie on or above the same correlation between star formation rate and stellar mass as other star-forming galaxies of the same redshift that we measured using Lyman break galaxies. That a galaxy whose observed Lyman alpha emission has restrum equivalent with greater than 240 angstroms is unlikely to possess a top-heavy IMF. But we need to test this spectroscopically, because it would be very exciting if some of them do. And finally, as far as we can tell, the Lyman alpha emitters at redshift less than 6 are faithful traces of large-scale structure, and the coast is clear to use them. Thanks for listening.
I have a very silly question. I'm a galactic observer of star-forming regions, redshift of very zero. We measure star-forming rate by counting. I know the YSOs down to like planetary mass, and then we have GM's giant molecular cloud mass as well. But in your case, not only generally, when I hear extragalactic talks, the star formation rate measurement, which you use for the star formation history.
Yes.
So how do you actually measure in your case? And then is it consistent for all the measurements, all these star forming rate measurement that I hear about? There are different diagnostic lines as far as I know.
Yeah, so we're not even using lines to measure star formation rates. You can do that, right? Going back to this diagram, these nebular lines, I think it's this one is H alpha. This is the H beta 03 complex.
Right.
So H alpha is a good star formation rate indicator. If you can correct it for the Balmer vector with H alpha and H beta, or use JWST to go to Paschen lines, it's even better. But we're not doing that. We're really inferring this from the shape of this broadband probe spectral energy distribution. And so there it's that the young stars contribute here. The easiest way to think about this, and I don't have that slide, is if you go into FSPS and you run for a stellar population of age 10 million years, you run for a stellar population of age 20 million years, and you just keep going, they're all a little bit different.
Right.
So they essentially form a series of basis functions, and then you take the observed SED and you decompose into how much of each is needed to make it. That's our star formation history.
So I would like to connect in a way that like there are locals, that way, and then the way we are measuring,
Yeah.
and then check the consistency.
Yes,
That's why
great.
I was, yeah.
We actually undertook an attempt at that, but using something a little less thorough than what you do. because there are color magnitude diagram-based star formation history estimations for local dwarf galaxies. A lot of work has been done on this, including by my colleague at Rutgers, Christy McQuinn. And so in a paper led by Charlotte Olson that came out in 2021, we actually took dwarf galaxies that had broadband spectral range distributions and color magnitude diagrams, and we compared those two methods of estimating the star formation history. We found a systematic shift of about 1 billion years in when we think events are occurring versus that, but otherwise some really interesting features, including the idea that within 4 megaparsecs of the Milky Way, all of the dwarf galaxies seem to have undergone a drop in star formation 6 billion years ago and a rejuvenation 3 billion years ago. So check out that paper.
Yeah.
I don't know how to use YSOs to do
I'll
that, because those are a few megaparsecs away, but we did attempt a comparison like that, and we found something really interesting.
Thank you.
Any other questions for Eric?
Otherwise, I'll be around.
Stop by his office and let's thank him again.